Today we've got a really cool cosmic detective story for you. It's a mystery that has been bugging scientists for decades, and it involves incredible power, massive cycles, and a really fundamental question about how our own star, the sun, basically cleans its house. So, here's the mystery we're tackling. We know for a fact that the sun's entire magnetic field does a complete flip-flop about every 11 years. But for that to even happen, it first has to get rid of the old magnetic field. I mean, think about it. Where does all that leftover energy actually go? That is the question at the heart of our investigation.
Yeah, you can really think of this as the ultimate cosmic housekeeping problem. Before the sun can even start generating a brand new magnetic field for the next cycle, it has to somehow sweep away these enormous leftover magnetic structures from the last one. So how exactly does a giant star take out its magnetic trash?
Okay, so the fancy scientific term for this old energy is toroidal flux. The easiest way to picture it is to imagine these colossal, invisible bands of magnetic energy just wrapped around the sun's guts. They're like a giant, tightly wound up rubber band holding a ton of energy from the old solar cycle. And this is the stuff that has to go.
All right, so to crack this case, scientists have come up with three main theories. Or, for our investigation, let's call them our three main suspects. Each one describes a totally different way the sun might be getting rid of all that old toroidal flux.
So who are they? In the lineup, we've got cancellation, diffusion, and emergence. Let's dig into what each of these suspects is all about.
All right, first up, we have suspect number one, cancellation. This idea is pretty straightforward. It suggests that as the sun starts building its new magnetic field, the new field has the opposite polarity. So when the new blue field meets the old red field, they basically just zap each other out of existence. It's like adding a -5 to a +5. They just cancel out and become zero.
Next in the lineup is diffusion. Now this is a much more chill, passive process. The theory here is that the old magnetic field isn't actively destroyed or anything, it just kind of leaks away. It slowly dissipates over time, a lot like how smoke just gradually clears out of a room on its own until poof, it's gone.
And that brings us to our third and maybe most dramatic suspect, active region emergence. This theory is way more active. It proposes that the toroidal flux is physically ejected, thrown out from the sun's interior, and its escape hatches? Sunspots. In this version of events, sunspots are like these giant pressure release valves, literally venting all that old magnetic energy out into space.
Okay, so we've got our suspects lined up. But how on earth do you test these theories? It's not like you can just fly a spaceship into the sun's core. Well, scientists at Shandong University did the next best thing. They built an incredibly sophisticated virtual sun on a supercomputer, feeding it over 100 years of real solar data.
And this is where things get really clever. They ran their supercomputer simulation 3 different times. In the first run, they basically told the simulation, okay, cancellation is the main way you get rid of old energy. In the second run, diffusion was put in charge. And in the third, emergence was the star of the show. This let them see which process created a virtual sun that actually looked and acted like the real one we see every day.
But, what does behaving like the real sun actually mean? Well, for any of these suspects to be the real deal, their simulation had to perfectly recreate 2 key behaviors that we have observed for decades on the actual sun. These are our crucial real-world clues, the ultimate litmus test. First up, clue number 1, the famous butterfly diagram. The simulation had to show sunspots popping up at the sun's mid-latitudes at the beginning of a cycle and then slowly drifting towards the equator over 11 years. This makes a really distinct pattern that looks like butterfly wings. It had to match that. Clue number 2 is the predictive link. See, for decades we've known that the strength of the sun's magnetic field at its poles at the end of one cycle is an amazing predictor of how strong the very next cycle is going to be. The simulation absolutely had to nail this cause and effect relationship.
Okay, the stage is set. 3 simulations, each one run with a different suspect in charge, and the results of each were checked against our 2 non-negotiable clues from the real world. So, who's the real culprit? Let's look at the evidence.
And wow, the results were just crystal clear. Cancellation? It failed both tests. Big red X's all around. Diffusion actually managed to pass the prediction test, which is interesting, but it totally failed to create the butterfly diagram. And then there was emergence. It passed both tests with flying colors.
The takeaway here is just massive. The evidence is totally unambiguous. Only one of our suspects, active region emergence, was able to create a virtual sun that behaved just like the real thing, hitting both of our crucial real-world checkpoints.
And don't just take my word for it. The scientists who ran the whole thing, Zhang and Chen, put it perfectly in their paper. They said, "We conclude that active region emergence dominates the subsurface toroidal flux loss." Case closed.
All right, so this is super cool, right? We've cracked a huge cosmic mystery. But you might be asking, so what? Why does understanding the sun's magnetic plumbing actually matter for us way back here on Earth?
Well, it matters a lot. For starters, this shows us that sunspots aren't just some passive blemishes on the sun's face. They are active, absolutely essential parts of the sun's engine. They're the exhaust ports for the entire magnetic cycle. By confirming this, we get a way clearer picture of how our star actually works. And that understanding leads directly to better predictions about how strong future solar cycles will be. And that prediction is critical. I mean, really strong solar cycles can create monster solar storms that can knock out our satellites, fry power grids, and endanger astronauts. So better predictions mean better protection for all of us.
So really, the next time you see a picture of a sunspot, try to remember what you're actually looking at. It's not just some temporary dark patch. It's a massive exhaust vent for the sun's colossal internal engine, physically clearing out the old junk to make way for the new 11-year cycle to begin. It just makes you wonder, right? What other profound secrets is our star just waiting for us to uncover?